Now that we've interpreted a couple of partial derivatives, let's talk about how to actually take partial derivatives. So first off, you'll be given a function of several variables. In this case, we'll start with a function of two variables. In order to take a partial derivative, whatever you're treating as your variable, you'll treat as a variable, and any other variable is going to be treated as a constant. So for example, if I'm interested in taking the partial derivative of f of xy is equal to x times the sine of xy with respect to x, let's start there. So partial derivative of f with respect to x, or probably the preferred notation, f with a subscript x of x and y. And we'll just make a little note here that says treat y as you would treat a constant. So when I see what we have here, what I'm really seeing is x times the sine of x times a constant. So we're treating x as the variable, we're treating y as a constant. So first off, I notice that we have x times another function of x, so we'll make use of the product rule. So this will be the first function times the derivative of the second function. And by derivative, I mean partial derivative with respect to x, plus the second function times the partial derivative with respect to x of the first function. Now, one of these is going to be pretty straightforward to simplify. This will be x times. Here, we're going to be making use of the chain rule. We have a function inside of another function, and we don't just have x in here, we have x times, well, what we're treating as a constant. So we'll start with the derivative of the sine function, that'll be the cosine function, inside stays the same, and then we multiply by the partial derivative with respect to x of that inside function, plus the sine of xy times the partial derivative of x with respect to x, which would simply be 1. Now for the partial derivative of x times a constant, you could think of this as the derivative of 5x or 3x or 70,000x. Regardless of that derivative, you are going to be simply left with whatever the constant was. So power rule for x says multiply by the 1, power goes down to 0, and this will just be y times 1 left over. And we'll have a sine of xy left over here. So final answer, if I'm going to reorder this a little bit, would be x times y times the cosine of xy plus the sine of xy. That would be our partial derivative with respect to x. Now for a partial derivative with respect to y, first off notation, df over dy, or using the subscript notation, partial derivative of f with respect to y of our function of x and y. So here we'll be treating y as though it's our variable, so we are going to treat x as a constant. So with that in mind, to interpret the original function, this is now a constant times the sine of a constant times y. So in my mind, I'm thinking to myself, how would I differentiate something like 5 times the sine of 5y? Well, that initial constant, or that initial 5, or that initial x in this case, would simply be a constant multiple, and thus can be ignored. For the derivative of the sine function, that'll be the cosine function, and once again we'll be applying the chain rule, but this time it'll be the partial derivative with respect to y of the inside. So once again, this is going to be the derivative of a constant times y with respect to y. And just like we did right back up here, if you're taking the derivative of a constant times a variable, you'll be left with simply the constant. The constant in this case being x. And if we're going to reorder this to try to make it a little nicer, that'll be x squared times the cosine of xy. So treat your one variable as though it's a variable, treat all other variables as though they are constants. Let's try out one more example. This time though, we're going to be working with a function of 3 variables. This is going to be f of, the 3 variables are r, s, and t, and it's going to be r squared times e raised to the s over t power. So we'll see 3 pretty different partial derivatives for this one. So first partial derivative that we'll do will be the derivative of f with respect to r. So df over dr I feel like there was a Roosevelt reference in there. FDR. Oh yeah, FDR. Yeah, Franklin Delano Roosevelt. So for this partial derivative, we are going to treat s and t as constants. The only variable that we recognize here is r. So really what we're doing is we're taking the derivative of r squared times, well, that e to the s over t power would just be a gigantic constant. Now in this case that would be a constant multiple, so we'll just go ahead and leave that multiple in there and differentiate the r squared with respect to r. That would be 2r. Reordering to see kind of a better order here, we'll get 2r times e raised to the s over t power. Looks kind of like to rest. Yes, I want to rest for a final answer. Wow, that's deeper than I wanted it to be. So for the next one, partial derivative of f with respect to s, or f with the subscript s of r, s, and t. This time we are treating s as though it is our variable, and so we are going to treat r and t as constants. So treating r and t as constants, what we're seeing here is a constant times e raised to the s over a constant power. So given that r squared is a constant multiple, we're going to ignore that. We'll differentiate e to the s over t. Derivative of e to the is going to be e to the, but then the chain rule says multiply by the derivative with respect to s of s over t. Now, similar to what we did on the previous problem, we can treat this as 1 over t times s, where 1 over t is simply a constant multiple. So taking the derivative of a constant multiple times a variable will just give us the constant multiple. That would be just 1 over t. So reordering to try to make this look a little bit nicer, we'll call this r squared over t times e raised to the s over t power. So one more partial derivative for us to take is going to be the partial derivative of f with respect to t, or f with a subscript t of r, s, and t. For this one, we're treating t as though it's our variable, so we are going to treat r and s as constants. So with that in mind, we are looking at a constant times e raised to the constant over t power. So similar to what we saw for the last one, we're going to start by treating r squared as a constant multiple and ignoring it. Then we'll differentiate e to the, and that'll give us e to the. And then we're going to take the derivative with respect to t of that numerator. Now, in anticipation of making this a little bit nicer, we're going to call this s times t to the negative 1 power, so that we can treat s as a constant multiple and apply the power rule to the t. So once again, r squared times e raised to the s over t power times. S is a constant multiple and can be ignored. T to the negative 1 power, we apply the power rule. We get negative t to the negative 2 power. Now reordering that so that all of the other variables come out front, we'll call this r squared times s divided by t squared, and give it a negative coefficient as well. The e to the s over t power stays the same. That'll be our final answer for the first partial derivative of f with respect to t.